time, we ended with a discussion of the oxygen dissociation curve. And we showed that it was a sigmoid curve. We showed that it had a slope of 4 that indicated that there were 4 oxygen binding sites on each of the hemoglobin molecules. And we closed with the idea of the rightward shift, or the leftward shift for that matter, of the oxygen dissociation curve, and that the movement of that curve, either to the right or left, contained information about whether the hemoglobin had a higher or lower affinity for the oxygen. A rightward shift said that the hemoglobin had lost some of its affinity for the oxygen, and the oxygen was more likely to leave the iron in the hemoglobin. We thought of that intuitively when we described how if we increase the heat, if we increase the temperature, then that increase in temperature is going to signal, that vibrational energy is going to signal the oxygen to be shed from the iron atoms. If we cooled the temperature down and had less vibrational energy, then the oxygen would bind more tightly to the iron. So we had a temperature effect, where increased temperature reduced the affinity of the iron for the oxygen, decreased temperature increased the affinity of the iron for the oxygen. Well, we're going to play that same game today, but now we're going to repeat that story under the control of pH. Just as we saw a change in the affinity of the hemoglobin under circumstances of changing temperature, we're now going to see a change in the affinity of the hemoglobin under changing acid environments, or pH. We're going to see that lowering the pH produces a rightward shift. So we'll walk through this simply describing the rightward shift resulting from a lowering the pH, which of course is an increase in hydrogen ion. But that increase in hydrogen ion results almost entirely from the increased carbon dioxide that's generated in the tissues. We'll walk our way through today many of the aspects of the chemistry of carbon dioxide in the blood. And one of the first places we'll describe here is how carbon dioxide in the blood is going to shift the pH. The carbon dioxide in the blood out in the tissues is going to lower the pH. Now, in the latter part of the 19th century, there's a guy named Christian Bohr. And he figured this out. He was a Dane. He was, in fact, the father of Niels Bohr, who was the father of quantum mechanics. But Christian Bohr was the first to recognize that if you lowered the pH in blood, that reduced the affinity of hemoglobin for oxygen. He didn't know the organic chemistry or the molecular biochemistry of that, but he recognized that lowering the pH tended to lower the affinity of hemoglobin for oxygen. He also recognized that most of that lowering in pH was going to arise because of carbon dioxide. So now this story begins to fit together. Carbon dioxide will be generated in the tissues. Carbon dioxide is the waste product of oxidative phosphorylation. When oxygen molecules accept an electron in the electron transport chain, the byproduct is the generation of carbon dioxide. This carbon dioxide then will diffuse out of the mitochondria and out into the cytoplasm and eventually out into the blood. And in the blood, that carbon dioxide will undergo a chemical reaction. We're going to see that the carbon dioxide plus water generates bicarbonate plus hydrogen ion. In the first explanation of this, it's the hydrogen ion that's going to be the major player. It's the hydrogen ion which is going to affect the hemoglobin to change its shape. The hemoglobin will actually bind the hydrogen ion. The hemoglobin is going to be a major buffer for hydrogen ion. But in the process of binding the hydrogen ion, the hemoglobin will change its shape and reduce its affinity for oxygen, thereby giving up the oxygen. So again, it makes sense. Lower pH, higher CO2. We want to get rid of that. We want to release the oxygen from its binding to the hemoglobin so it now can bind to myoglobin in muscle and also go to the mitochondria where it can be used to make energy in the form of ATP. What we'll see here is that the major chemistry is pretty much like the chemistry we talked about the other day when we had carbon dioxide dissolved in water. But in that case, where we bubbled carbon dioxide in water and made bicarbonate and hydrogen ion, and we made carbonic acid. What we're going to see here today is that there's an enzyme to do that. The chemistry is the same, but there's an enzyme that increases the rate of converting carbon dioxide and water into bicarbonate and hydrogen ion by 1,000,000-fold. And the wonder of that enzyme is that not only does it push carbon dioxide and water to bicarbonate and hydrogen ion, but under other circumstances, it can convert bicarbonate to hydrogen ion, bicarbonate plus hydrogen ion to CO2 and water. So the reaction goes in both directions. One of the ideas we'll run into as we work our way through this is that in blood, most of the carbon dioxide is going to be carried by bicarbonate. Something like 70% of the carbon dioxide in blood is carried as bicarbonate. There's another 7% which is carried as dissolved carbon dioxide, and the remaining 23% is largely bound to the hemoglobin at the carboxy ends of the proteins. So once we've gotten through this idea, the concept of carbon dioxide serving to lower the blood pH in the process of lowering blood pH, telling the hemoglobin to relinquish its oxygen, we're then going to loop back through another function of carbon dioxide. And that is, carbon dioxide is essential to us in determining the urge to breathe. The question here is, what drives your urge to breathe? As you're sitting here quietly, the urge to breathe is largely the result of carbon dioxide that's dissolved in the blood. Then from the blood, it moves into the cerebrospinal fluid in the brainstem. In the brainstem, the carbon dioxide, by its chemical nature, is converted to hydrogen ion and bicarbonate. The hydrogen ion now becomes the major signal. It's the hydrogen ion in the cerebrospinal fluid that will bind to sensory neurons. And those sensory neurons then are activated to fire action potentials, and through a circuit, that activity in the sensory neurons will tell interneurons, and then finally upper motor neurons, and finally lower motor neurons tell you to contract your diaphragm and breathe. And so this is, as you're sitting there quietly, will largely drive the urge to breathe. That's the CNS effect, but there's also a peripheral nervous system effect. And the peripheral nervous system effect results from chemosensors. There are chemoreceptors found in the aortic arch and in the carotid body. Now immediately when you think aorta and carotid, recognize that you're on the arterial side. So this is blood that's come out of the left side of the heart. So this is blood that's going to be highly oxygenated. And if things are working right, the blood should have been well scrubbed with carbon dioxide as the blood passed across the alveolus. So under normal circumstances, we're out here in the arterial blood. PO2 levels ought to be about 106 millimeters of mercury. PCO2 levels ought to be around 40 millimeters of mercury. We're going to see, though, when we start to exercise, we now change the dynamics. As we begin to exercise and generate more CO2 from exercise, some of that CO2 will spill over into the arterial side. So we're no longer at 40 millimeters of mercury. We start getting up to 42, 43, 45, and a little more. And that's now a signal to these chemosensories in the carotid body and the carotid arch to start firing action potentials. And they then will be the chemosensors that drive your breathing centers in the brain. And then your breathing centers in the brain now are being driven to some extent by these chemosensors in the periphery. The carbon dioxide chemosensors are actually pretty sensitive. And so you'll start a few millimeters of mercury change in CO2, and these guys will kick in. But on the other hand, the effect of oxygen, there are also oxygen receptors, chemoreceptors, in the aortic arch and the carotid body. But the oxygen receptors are not nearly as sensitive. And we'll see that to get these guys to begin to fire action potentials, the PO2 levels have to be down around 60 millimeters of mercury. So remember, the PO2 levels returning in the venous blood are at 40 millimeters of mercury. So this means that you're doing a terrible job of oxygenating the blood, and you don't bring in the O2 sensors. You don't bring in the O2 sensors until you're in a pretty bad pathologic state. But these guys are functioning more or less when you start to exercise. There's some indication even for well-trained athletes that the well-trained athletes will start to ignore this, because apparently when you're really exercising over long distances, you use a lot of energy breathing. And so well-trained athletes will learn to regulate this sensory input from the chemoreceptors, sort of suppress it, so that they won't use the CO2 levels to elevate breathing too high and use too much energy in breathing. But we're not going to get much into that detail. That's an exercise physiology point. So what we want to do, though, is we want to start here with our oxygen association / dissociation curve. This is where we left off on Friday, where we plotted PO2 and we plotted percent saturation of hemoglobin. And we said that it generated a classic sigmoid curve with a slope of 4. We said this was the Hill coefficient. That simply told us two things. First, that it said that there were 4 binding sites for the oxygen, and it also, because of the sigmoid shape, said that there was cooperative binding. And where we finished was to describe a rightward shift in the curve, where we could show an almost identical curve, but it was right shifted. And we said if we would draw a dotted line here for percent saturation and run them through these two, we would find that the percent saturation here is now the same at a lower PO2 for the black line than for the red line. Simply saying that the rightward shift is saying there is a lowered affinity of hemoglobin for oxygen. It's simply telling us that we're more likely with a rightward shift for the hemoglobin molecule to give up oxygen. And the way we describe this is that a rightward shift would result from increased temperature. And that was intuitively obvious, because if we increased the kinetic energy in those hemoglobin molecules, they were vibrating faster, they were more likely to shed their oxygen. And by the same token, we said we could have a leftward shift. And a leftward shift, the leftward shift indicated a higher affinity of hemoglobin for oxygen. Again, it makes sense if you can do this with a colder temperature. But what this is saying is that by changing the characteristics in the environment for the hemoglobin molecule, we can change the probability whether that molecule will hold on to the oxygen or whether it will give it up. We're going to see here, and I may as well draw this in a separate curve, that there's another way. Let's label this as temperature effect. On oxygen dissociation or association curves. Now we're going to redraw the same thing. And now we're going to label this as pH effect on O2 association. With hemoglobin. Well, here's PO2, and there's percent saturation. It's our standard curve, maybe a little steep. But now we see that if we lower blood pH, and remember from chemistry, lowering the blood pH simply means more acidic. That it's the increase in hydrogen ion concentration. What we find is that if we lower the pH, we get this classic rightward shift. So lower pH generates a rightward shift. And just as above, what that rightward shift says is you're more likely to give up the oxygen from the hemoglobin. Well, the next question to ask, of course, is there a biological origin for this hydrogen ion? Can we think of a place where we would generate hydrogen ion? It's no surprise where we're headed here is to describe the idea that carbon dioxide plus water gives rise to H2CO3, which gives rise to hydrogen ion plus bicarbonate, HCO3 negative. At this point, it's worth making a list. And that's to say that some 70% of CO2 in blood is carried as bicarbonate. Now, there's some other carbon dioxide here as well. There's about 7% that's carried as CO2 dissolved in blood. And the remaining, 23% or so, maybe a little less, is carried bound to the carboxy ends of hemoglobin. But the vast, vast majority of the carbon dioxide in blood is being carried as bicarbonate. From this equation, just this simple chemistry equation, you'll recognize that carbon dioxide in water gives rise to hydrogen ion. The hydrogen ion now lowers blood pH. This rightward shift that results from lower pH has a name. It's called the Bohr effect. And the Bohr effect, in its simplest version, simply says if we lower the pH around the hemoglobin is more likely to give up its oxygen. Christian Bohr also recognized that the predominant source of the hydrogen ion which caused this effect was because of carbon dioxide. So indirectly, an increase in carbon dioxide in the blood causes a rightward shift of the O2 dissociation curve, saying that the hemoglobin is more likely to give up its oxygen. Well, let's think about this intuitively. Where does carbon dioxide come from? Well, the source of CO2 is oxidative. It's oxidative phosphorylation. It's oxidative phosphorylation in mitochondria. So as we're using more oxygen, we're generating more CO2. So you can imagine places where we would be doing this. In the muscles, where when we're exercising really hard, we're using more oxygen because we're making more ATP, and in the process of making more ATP, the byproduct is carbon dioxide. The carbon dioxide then, in solution in the blood, lowers the pH, changing the shape of the curve to relinquish more oxygen at any given partial pressure. Again, it makes sense. If we're exercising, making lots of CO2, we want to give up more of the oxygen from the hemoglobin because the tissues are requiring more oxygen. So one of the sources for shifting the oxygen dissociation curve to the right is the hydrogen ion that's derived from carbonic acid. That's all true. The problem with the reasoning on it, though, the problem with the straightforward logic, is that this chemical reaction is remarkably slow. It takes a long time simply to do the chemistry of carbon dioxide plus water making carbonic acid, and then having it come apart into its component parts. Yeah, let me draw this, because we'll come back to this in a moment anyway. So now let's go back up to the upper panel and redraw the schematic diagram of the alveolus. And think about what's happening in the alveolus. So we can put some numbers to this. These will be the same numbers we talked about last week. So over here, we have labeled this as blood flow by the alveolus. And in our crude drawing of the alveolus, we imagine this as being a kind of box. Of course, it's more of a sphere. But conceptually, what we're thinking about is the idea that inside the alveolus is air. And from the discussion on Friday, you'll know that the PO2 levels are in the neighborhood of about 106 millimeters of mercury. That's the saturation point. But we also know that the PCO2 levels here are in the neighborhood of about 40 millimeters of mercury. Friday's discussion emphasized the role of hemoglobin in the pulmonary capillaries inside the erythrocytes. So last time we talked about the erythrocytes moving through the pulmonary capillaries, where this is a pulmonary capillary. And we said that the PO2 coming back from the tissues, remember the PO2 coming back from the tissues is in the neighborhood of 40 millimeters of mercury. But the emphasis last time was that when the blood would exit across this structure, headed back to the left side of the heart, then at this point the PO2 levels were in the neighborhood of about 106 millimeters of mercury. Perhaps a little lower up here, but at least probably close to 95% saturated. But we also made a point, and I'll show you this in blue, that the PCO2 levels in blood are in the neighborhood on the venous side of about 45 millimeters of mercury. And when the blood exits, they've come to equilibrium with the pCO2 levels in the alveolar space. So here, the pCO2 levels are in the neighborhood of about 40 millimeters of mercury. But yet the dwell time, the period of time when these erythrocytes are traversing by the alveolus, the period of time here is less than 0.75 seconds. When you're exercising hard, it's less than about 0.3 seconds. Now remember here that this 45 millimeters of mercury represents 70% of that 45 millimeters of mercury is being carried by bicarbonate. So this is coming through as HCO3 negative. In this brief period of time, we have to convert the bicarbonate back into CO2 plus water. Because it's the CO2 now that's going to diffuse from the blood into the alveolar space down its concentration gradient. My point here is mostly that what we have to do is really fast. We have to convert the bicarbonate into CO2 in less than 3/4 of a second. The problem with the chemistry that we have on the upper board, the problem of this inorganic chemistry is it's woefully too slow to do that. It simply can't keep up. So evolution, and it looks like several times independently, has developed a peculiar enzyme. And the enzyme is called carbonic anhydrase. Now, what carbonic anhydrase does is carbonic anhydrase can take carbon dioxide and convert it into bicarbonate and hydrogen ion. That's the same as the equation up here because this runs in both directions. But this now converts carbon dioxide to bicarbonate and hydrogen ion about 1,000,000 times faster than this slow reaction. So we've sped it up a whole lot. But not only is it moving in this direction, but the carbonic anhydrase now can take bicarbonate plus hydrogen ion to give rise to CO2 plus water. So we go back up to our upper panel. We can diagrammatically show this to say, in tissues, so for instance, if this were muscle, and you imagine a capillary in muscle, under these circumstances, oxygen leaves hemoglobin. Oxygen leaves the hemoglobin and goes out into the muscle. Meanwhile, carbon dioxide is coming back into the capillary because carbon dioxide is the byproduct of oxidative phosphorylation. So out of the muscles, we're relinquishing the oxygen and bringing on CO2. The CO2 now is the signal in the upper panel to lower the pH. But it's not the carbon dioxide directly, it's the hydrogen ion. So that we convert carbon dioxide to carbonic acid, and we have hydrogen ion, then this carbon dioxide in the muscle is telling the hemoglobin to give up more of its oxygen. And intuitively this makes sense. If we're exercising hard, we need more oxygen to go to the tissues. The byproduct of CO2 now is telling the hemoglobin to give up more oxygen, but it's not the CO2 directly, it's the hydrogen ion. And the hydrogen ion is coming from the role of carbonic anhydrase to rapidly make this hydrogen ion. Now this hydrogen ion will then be buffered by hemoglobin. There are mostly histidines in the hemoglobin that will bind to that hydrogen ion. So this is a really, really important enzyme. And what it's working, when it's working properly, back here in the pulmonary capillaries, we're now converting bicarbonate to CO2. So one of the most common enzymes in erythrocytes contain carbonic anhydrase. Carbonic anhydrase out here in the tissues is making hydrogen ion so that the hemoglobin will relinquish its oxygen. But back here in the pulmonary capillary beds, now the carbonic anhydrase is converting the hydrogen ion and the bicarbonate back to CO2 and water, also pushing that curve back in the other direction. So now we've increased the affinity for oxygen in the lungs. So everything is working to maximize oxygen binding in the lungs and minimize oxygen binding out in the tissues, both from the perspective of pH and the perspective of temperature. Now, I'm going to tell you a little bit of organic chemistry here, and I do this mostly because this was kind of a revelation to me about how carbonic anhydrase worked. And because it gave me an intuitive sense about how it works, I'll spend a minute here talking about the wonders of nature and how this enzyme increases the rate of a chemical reaction by 1,000,000-fold. And to begin this story, we're going to talk about zinc ions. In carbonic anhydrase. So in the middle of this carbonic anhydrase molecule is this zinc ion. And you may remember that I told you early on that one of the characteristics of any time we put a metal ion into a protein, we coordinate it with these nitrogens on pentameric rings. You remember this was the structure we talked about when we talked about hemoglobin. But in the case of hemoglobin, there were 5 nitrogens on these histidines. And hemoglobin, you remember, there was an iron, and that there were 4 nitrogens coordinating with it. You'll notice here there's an open spot. There isn't a 4th histidine at this point. Instead, at this point, at this zinc, because the zinc now, because of the coordination, this zinc has like a triple positive charge to it. So it's highly positive. Because it's so highly positive, it will interact with water. Remember, there's plenty of water around. So there's the oxygen. And then there are the 2 hydrogens. We're back to the dipole moment of water again. The dipole moment on water, remember, this negative end, the partial charge on oxygen is negative. So it's really attracted to the zinc. So the electrons now whirling around the oxygen, being attracted to the zinc, are now going to basically steal those electrons from this hydrogen. This hydrogen doesn't have electrons very often, so basically this hydrogen just wanders off. It wanders off as a proton, so that's the source of the proton This is where the hydrogen ion comes from. Meanwhile, this hydroxyl now, because it's drawn its electrons over here, is extremely negatively charged. And it now becomes what is known as nucleophilic. And the nucleus it's looking for, in fact, is carbon dioxide. So right next door to this zinc, there's a binding pocket for carbon dioxide. And when this becomes so electronegative, all these free electrons, it will now interact with the CO2. When it interacts with the CO2, it gives rise to HCO3 negative. Now it's worth taking a moment to recognize that the OH is from water. It's this hydroxyl. But then there is the CO2. And you count them up. There's the H. There's the C. And now 1, 2, 3 oxygens. So that's HCO3, and we end up with a negative charge on it. So in this way, we have increased the rate of production of bicarbonate out here in the tissues, carrying most of the blood back to the lung as bicarbonate. Then in the lung, this reaction goes the other direction. In the lung, we take bicarbonate through the effect of carbonic anhydrase, and we convert the bicarbonate into CO2 plus H2O. We reverse the reaction, and now the CO2 in the lung can be moved across the alveolar space and out into the air. We can breathe in and out and get the carbon dioxide to leave the lung to the outside world. So any questions about that? So now we're beginning to see the effect of pH through carbon dioxide on a rightward shift of the hemoglobin to give up its oxygen. We're now seeing we can return that system back to normal pretty much in the alveolar space by using carbonic anhydrase to run the reaction in the other direction. But there are other functions of carbon dioxide, and that's where I want to head here. I'm going to leave this up because we're going to use that in a moment. And this part of the panel, I want to describe the role of carbon dioxide and the urge to breathe. It's a bad day. So this is CO2 and the urge to breathe. Now in this case, we're going to be talking about capillaries in the brainstem. So what I'm trying to draw here is a schematic of a capillary, a blood capillary, in the brainstem. Now you remember that in the plasma, we have about 7% of the carbon dioxide as dissolved. And the carbon dioxide dissolved, now the carbon dioxide will come across the blood-brain barrier and out here into the extracellular space. Of the brainstem. Now, the extracellular space contains something known as cerebrospinal fluid. And when the carbon dioxide, some of it, small amounts, diffuse out across the capillary, now we have CO2 in the cerebrospinal fluid. We don't need to invoke the rapid chemical response of a carbonic anhydrase. We can take the CO2 and in the cerebrospinal fluid take CO2 plus H2O give up bicarbonate plus hydrogen ion. It's this hydrogen ion now that becomes the most important player. The hydrogen ion in the brainstem will bind to sensory neurons. The hydrogen ion tells these sensory neurons to generate action potentials. These sensory neurons, with their regular action potential rate, is working through a circuit. There'll be some interneurons. Some of those interneurons then will finally synapse onto upper motor neurons, the upper motor neurons of the brainstem. Those upper motor neurons will synapse onto lower motor neurons in the cervical spinal cord. And those lower motor neurons now are going to innervate the diaphragm. So the hydrogen ion, through this sensory neuron and that circuit, is telling you to activate your phrenic nerve, activate the lower motor neurons in the phrenic nerve to tell the diaphragm to contract. That's why we have to have hydrogen ion to tell us to breathe. Well, as you're sitting there, most of your urge to breathe is coming from that hydrogen ion. Now, let's walk this through, because this is actually something that has happened to people around here. Let's imagine now you're standing on the edge of the pool and you want to swim underwater as long and as far as you possibly can. And so you have this brilliant idea that what you'll do is you'll hyperventilate. You'll breathe in and out really fast. So you'll pant effectively, breathing in and out really, really fast, in the hopes that you'll increase the number of hemoglobin molecules that are bound to oxygen. Well, we know that's stupid, because at this point we know that in regular breathing we'll fully load the hemoglobin with oxygen. So we haven't had any effect on the loading of hemoglobin with oxygen by breathing in and out fast. But what we do is we take the PCO2 levels. By breathing in and out fast by hyperventilating, this number now can become smaller. It may go from 40 down to pick a number, 25 millimeters of mercury. Well, now we come to equilibrium, where the old equilibrium was 40 millimeters of mercury. Now the new equilibrium is 25 millimeters of mercury. This is basically a reflection of the concentration of CO2. So now we have less CO2 available to come into the cerebrospinal fluid. We have less CO2 to generate hydrogen ion in the cerebrospinal fluid. We have fewer hydrogen ions to bind to the sensory neurons, so we suppress the urge to breathe. And this happened to a fellow about 15 years ago here. He was on the edge of the pool. He wanted to swim as far as he possibly could, so he hyperventilated. He dived into the water, began to swim, and he swam, and he swam, and he swam, and he used up all of the oxygen on his hemoglobin molecules. So the oxygen levels in his blood plummeted, so he didn't have enough signal in his brain to tell him to stay awake. He went unconscious. So he went unconscious before he had the urge to breathe. But he did get the urge to breathe back when he was underwater, and he drowned. So this actually is a fairly common event. People hyperventilate before taking a long dive, and in the process, what they do is they suppress the urge to breathe, and underwater, that's a big problem. In the final few minutes, let me talk about the peripheral chemoreceptors. What we've emphasized here is the role of hydrogen ion in the brainstem. And almost all the time when you're just sitting around, this is what you're using. But there are circumstances where we'll start using changes in the carbon dioxide level as they exit the alveolar region. Now remember where this blood's going. This is pulmonary capillary. So this blood is headed to the left side of the heart. It's going to go out into the aorta and into the carotids. So now we want to think about what's going on with PCO2 levels and PO2 levels in the aorta and in the carotid bodies. Let's go to the upper panel. And here what we're going to start talking about are the chemoreceptors, the peripheral chemoreceptors for carbon dioxide and for oxygen. So in the upper panel, we talked about the central effects, but here we're going to talk about the peripheral effects. So we'll take this panel and describe chemosensors. In the carotid body and the aortic body. The chemosensors monitor CO2 and they monitor O2. But as we look at these chemosensors in the peripheral nervous system, recognize that they're in the carotid body and in the aortic body, and the blood in these regions is oxygenated. Oxygenated blood from the left heart. So first let's talk about the CO2 receptors, because they're probably in everyday life play a more important role. If you go out this afternoon, you go for a long run, and you start to feel yourself breathing faster and faster, that more rapid rate of breathing largely comes from the CO2 receptors in the chemoreceptors in the carotid body and the carotid artery. I'm sorry, carotid artery and the aortic body. And so what these guys begin to do is they begin to recognize increasing CO2 levels. But let's go back to the upper panel, because when you're at rest, it's pretty straightforward to come back to the old 40 millimeters of mercury for carbon dioxide and use that basal carbon dioxide and hydrogen ion effect to tell you to breathe. But now when you're starting to exercise hard, now you're generating more CO2 in the tissues. More CO2 is coming back here. And if you haven't increased your heart rate to make the blood move through here more quickly, what will happen is your CO2 levels will now begin to creep up. So the CO2 levels in the arterial blood begin to get higher and higher. So now they go from typically 40 to maybe 42, 43, 44, 45. And at that point, once we get up into the mid-40s, then on the arterial side, we're now activating these CO2 sensors to tell you to breathe. That's a pretty strong drive. And you will, in fact, tell yourself to breathe with these CO2 sensors. But the O2 sensors are a little different. The O2 sensors are monitoring oxygen. But their electrical activity, the increase in action potential rates, don't go up very much until we get into the range of about 60 millimeters of mercury, PO2 levels of 60 millimeters of mercury. Well, you come back to our upper panel, and you'll recognize that PO2 levels coming back from the venous blood are down around 40. If things are working right, we ought to have PO2 levels going out to the left heart of over 100. But under these circumstances, we're saying those peripheral chemoreceptors don't kick in until we're about 60 millimeters of mercury. That means something terrible's happened here. That means perhaps you filled your lungs up with water, so you have pneumonia. Maybe you're on top of Mount Everest. At Mount Everest, you will, in fact, start getting PO2 levels that are low enough to signal you to breathe. But under normal breathing circumstances, you use this system of CO2 and hydrogen ion. And it's only under extreme cases you use oxygen sensors at all. But your PCO2 levels will, in fact, influence the chemoreceptors to tell you to breathe. And let's let it go at that, and we'll start on the renal system on Wednesday.